Everyone, my name is Nong Da. I'm from Jiangsu University of Science and Technology. Today we talk about numerical simulation of interaction between ships and breakwater by using OpenFOAM. I talk with this sixth part about research. The first, for ships floating in a port or harbor, the interaction between field and the ships are significant, especially when their breakwater is sailed before it. In the berthing process, the distance between the berthing vessel decreases continuously and the hydrodynamic interaction increase, resulting in large motion response of the barges. It is essential to understand the advanced hydrodynamic phenomenon of gap resonation in actual berthing operations by researching the response of breakwater cover port area to wave environments of different periods. The part two is numerical model. The research using the OpenFOAM version 2206 for numerical simulation, and we use waves to form toolbox to achieve wave generation and absorption and to regulate the initial conditions. The Rain's equation is incompossible viscous fluid flow into phase is solving using the interform solver. The movement of interface between air and water was captured using the VOF method. The pressure and the velocity computing the solved using the pinball algorithm. Three is computational domain and boundary conditions. This figure is about the describes the calculation model of the numerical tank. It's composed of two identical square barges. We named barge A and barge B and breakwater. The water depth we said is 20 meters. And the wave generation relation zone is set at front 2 to 4 wavelengths of the breakwater, and the wave absorption relation zone is set at 1 to 3 wavelengths after the part B. Both the relation zone is 2 wavelengths long. And the left side of the barge A is placed at the position of 2 wavelengths behind the breakwater. And we set 40 wave height gauge at the blue dashed lines in this figure. This is the mesh about 2D numerical wave flume. In order to avoid the incurrent numerical simulation caused by sudden change in mesh size, arrange the encryption zone double the wave height up and down around the free surface. In the free surface encryption zone, a single wave height in the wave height direction was divided into 60 mesh cells. That is 32 mesh cells in the encryption zone of the wave height direction. And this two figure is the wave level time series about the different mesh and the different time steps. We set 4 different mesh in this table, and 4 different time steps in the right table. In the right table, T is the wave period, and N is the number of mesh cells in the wavelength direction. Simulate the wave number 3 and 4 cases are relatively close to the theory, but the number 4 does not improve the actuality of numerical simulation, but lead to the waste of calculation costs. Is that the same reason for number 3 and number 7 about the time step? Therefore, we choose the number 3 as the final numerical calculation mesh. This is the mesh about past research. We encrypt 2 wavelengths mesh before and after the breakwater, and 1 wavelength for budgets based on the empty water tank mesh. And figure A is describe the perimeter encryption mesh for only breakwater, and B is for only budgets. C is the global mesh of the numerical tank with both the breakwater and budgets. 4 it's about the simulation of breakwater and budgets. The transmission coefficient of the breakwater is calculated by measuring the water level at the distance of 2 wavelengths behind it. And in this figure, we can find that the transmission coefficient of 4 second period is only 1%. That makes the working condition meaningless for subsequent work. So we just research the 5 to 10 seconds period regulated wave condition in the following task. We select a regular wave with 5 to 10 seconds at the incident wave period and the 10 meters as the budget distance. The breakwater drift is 3 meters and the budget is 5 meters. The impact of object motion is not taken into account in this study, so we just immobilized the objects. The relevant phenomena are researched by comparing whether there is a breakwater in front of the budgets. So we set 4 working conditions about empty water tank, budgets only, breakwater only, and both the breakwater and the budgets in the wave tank. 5. The result and the discussion. In this figure, it's water level time series for the A is position at budget gap center, and B is at the 0.5 wavelengths behind the budget B. We can find that the gap resonance effect makes the amplitude of budget center waves evolution increase by nearly 70%, and the budget area free surface decreased by 27% compared with that only empty tank. And for budgets protected by breakwater compared with only a breakwater, free surface at the gap increased by 85%, and behind the budget B decreased by 20%. For budgets protected by breakwater compared with only budgets, free surface at the gap decreased by 68%, and behind the budget B decreased by 68%. This is the pressure nephogram near narrow gaps, and A is budgets without breakwater cover, and B is the budgets with breakwater cover. As we see in figure A, vorticities predominantly emerge and collapse in the vicinity of the narrow gap base, and the most intense vortex occurs in the lower right corner of budget A and the lower left corner of the budget B. To compare the figure A and B, it can be observed that under the influence of breakwater cover, there is a significant reduction in interclearance pressure compared to without the breakwater cover, and we found that the vortex basically disappears. This is a figure about velocity vector graphs near the narrow gaps. In figure 8, there is a significant velocity difference between the lower right corner of part A and the lower left corner of part B. Due to the periodic transmission of waves, the velocity vector changes periodically. The fluid vector velocity of free surface in gap changes synchronously with wave transmission. The velocity difference between the lower left corner of part A and the lower right corner of part B is sufficient to induce vortex formation. To compare the pressure nephogram and the velocity vectogram, is evident that the presence of breakwater significantly reduce the velocity of the flow field around the barges, resulting a remarkable decrease in the difference between the free surface and the periodically varying velocity. This eliminates occurrence of eddy current condition around the barges. Finally, the summary is that this figure is average wave level evolution altitude varies with the incident wave period at the position at graph center and 0.5 wavelength position behind the barge B. For barges under the shelter of breakwater, we can find the eddies around the currents are effectively eliminated after the breakwater is weakened. Due to breakwater cover barges wave energy attenuation, the elevation change of the free surface in narrow gap is reduced by 70% to 85%, which proves that the breakwater as well as the arrangement of ships can effectively dissipating the wave energy. Thank you for your listening. Did you consider the motions of the part? We consider this position as past research, and research may begin at next week. Next week. Other questions? So I have a simple question. Can you go back to the slide 15 or video 15? Yeah, it's fine. So for the left figure, the wave elevation for only case is the largest, right? Pardon? For the left figure. Left figure. Yeah, the wave elevation for the barge only case is largest. Why is that? Barges only the place is in the wave barges is in the barge gap center. So the location of the wave is in front of that. Inside the gap. Inside the gap. So where would the barges? Two barges have